Hello and welcome to 4.6 Optimization Problems. In this section we'll be looking at applications of the derivative that we could use to find extreme values. Okay, a lot of these have practical applications in many areas of life. For example, if you want to maximize the area of a garden, how big to make the length and width of a rectangular garden. A business person wanting to minimize costs and maximize profits. Anything that involves minimizing a cost or minimizing the amount of material used to making a packaging or maximizing the area of something. These are the types of problems that you'll be using to solve those types of problems. First thing, of course, you want to understand the problem. You want to be able to ask yourself, what's the problem looking for? What's given to me? What are the conditions? A lot of times, if you draw a diagram, it helps, get a visual of what it looks like. And then you want to introduce some notation, like A for area, H for height, T for time, things like that. Okay, so let's start off with a maximizing area problem. Okay, you have a farmer that has 2,400 feet of fencing and wants to fence off a rectangular field that borders a straight river. He needs no fence along the river. What are the dimensions of the field that has the largest area? Okay, so if you go through some possible lengths of fencing that add up to 2,400 feet, you'll see that you could have an area that looks like this. That's 100 by 2,200. Okay, gives us an area of 220,000 square feet. You could have an area that's 700 by 1,000. Okay, and its area is 700,000 square feet. You could have an area that's 1,000 by 400, and its area is 400,000 square feet. Okay, now oftentimes the guess and check model like this would be a little cumbersome, right? It'll take some time. You'll probably do a lot of guessing, a lot of checking. But there is a straight out way of trying to figure out what is the largest area. Okay, so to do that, let's come up with a diagram, a generic diagram for the area of the field. Okay, we label x and y, okay, for the two dimensions. Y will be the length, x will be the width. Okay, and we want to maximize this area. So now the area for this field, according to these variables that we have, would be area equals x times y, right? Length times width. Now we also know that the length for the fence is going to be 2,400, right? So the length, we got x plus y plus x. So in other words, we have 2x plus y. Let's do that first. X plus y plus x equals 2,400. Or in other words, 2x plus y equals 2,400. Now, for us to be able to maximize this area problem, it's easier for us if we had just an equation in terms of one variable. Okay, so this is the main equation that we're going to maximize. Now we have a secondary equation that'll help us. Okay, so secondary equation is this. So this is going to help us, all right, in terms of getting our variables in terms of one, getting our equation in terms of one variable. Okay, so if I want to get my equation in terms of x, I could solve my secondary equation for x, and then I could plug that in, and I could plug it in, actually I could solve it in terms of x, I could solve it for y, and then plug it in place of y, and then all my equation for my area will be in terms of x. Okay, so for example, I can subtract 2x from both sides. That'll give me y equals 2400 minus 2x, and then I could take this and plug it into y in my main equation. Okay, so x times y. Now in place of y, plug in 2400 minus 2x. Okay, and then you can now distribute the x. So area equals 2400 x minus 2x squared. Okay, so now what we want to do is we want to take the derivative of this. Okay, we want to take the derivative. Okay, with respect to x, dA dx would be, this will be 2400 minus 4x. Okay, and by taking the derivative, we could solve for a critical point. So set the derivative equal to 0, and now figure out what is x. Okay, so if we add the 4x to the other side and divide by 4, that would give us x equals 600. Okay, so that means at 600 feet we have a critical point. Okay, so now you could do a simple first derivative test to figure out what's going on at 600. Is it a maximum or is it a minimum? Okay, now you know you're not going to be able to go out to 2400. Okay, the most we could do here in terms of, if you want to figure out what's your domain for this function, you could look at your original function here, x, and then 2400 minus 2x. If you set it equal to 0, you'll see that x would equal 1200 and x would equal 0. Right, so let me show you guys that. If you had area equals x and then 2400 minus 2x, okay, set it equal to 0, that means you could have x equals 0, or you could have 2400 minus 2x equals 0, so you have x equal to 1200. Okay, so you could be at 0. Okay, your domain is going to be between 0 and 1200. Okay, so now pick a number between 0 and 600. See what that gives you for the first derivative. Okay, so let's say 500. Or we could go even smaller. We could do 300, let's say. And then for this one, we could do like 900. So if we plug that in, 300, 24, 4 times 3, that's 12. That's a positive 1200. Okay, so that's positive. And if we plug in 900, 4 times 9 is 36, 3600. 2400 minus 3600, that's a negative. So we go from increasing to decreasing. That means we have a maximum. Okay, we have a maximum at 600. Okay, so that means x is 600. Okay, so that means according to this is going to be 600. So the field will be 600 deep. And then plug it into here. 2 times 600, that's 1200, plus another 1200. So the length of the field will be 1200 feet. Okay, and this will maximize the area. Okay, so 600 feet deep and 1200 feet wide for the dimensions of the field. Okay, minimizing cost. A cylindrical can is to be made to hold 1 liter of oil. Find the dimensions that will minimize the cost of the metal to manufacture the can. Okay, so to figure this out, we draw the can. We have a figure here of the can. And we want to minimize the cost of the metal to manufacture the can. So the cost of the metal means we have metal for the top, the bottom, and we have the metal for the side wall. Okay, so that area, right, for that metal is what we're trying to minimize. Now we have for the base and the top, right, that's pi r squared, and then because there's 2 of them, there's 2, so 2 pi r squared plus, now area of the side wall will be the circumference of the top times the height, so 2 pi r times the height. Okay, that would be the area for our cylindrical can. Now they also tell us that the volume of the can is 1 liter. Now we're going to change that 1 liter into a smaller unit. We're going to do centimeters, cubic centimeters. So 1 liter is 1,000 cubic centimeters. And we know that the volume would be pi r squared right, the area of the base times the height. Okay, so we know that pi r squared times height is going to equal 1,000 cubic centimeters. Okay, so let's get this all in terms of r's. Okay, so in our maximizing or minimizing formula, okay, I'm going to rewrite this secondary equation. Okay, this is my secondary equation here in terms of h, so that I could plug in for h and I'll have my equation in terms of r. Okay, so to solve this for h, I could divide by pi r squared both sides. So I have h equals 1,000 over pi r squared. Okay, and that's what I will plug in for h. Okay, so let's do that. We have a equals 2 pi r squared plus 2 pi r times 1,000 over pi r squared. Okay, simplifying it a little bit, we'll have the pi's cancel here. we'll have an r cancel with an r here. The 2 will multiply with the 1,000. So we have a equals 2 pi r squared plus 2,000 over r. Okay, so in other words, a equals 2 pi r squared plus 2,000 times r to the negative 1. Okay, so now we want to try to minimize this. So let's take the derivative. Okay, so taking the derivative with respect to r, that would be 2 times 2, that's 4 pi. So we have 4 pi, and then taking the derivative here, we have minus 2,000 r to the negative 2. Okay, so what does that look like? That means we have 4 pi minus 2,000 over r squared. Okay, 4 pi r. Now what we can do, get it to look like a single fraction. So this one on the left we can multiply by r squared over r squared. Okay, so we have 4 pi r cubed minus 2,000 all over r squared. Now we want to set this equal to 0. And then solve for r. So now if we take this top part, right, because the only way this will set it equal to 0 is if we take this top portion, set it equal to 0. So 4 pi r cubed minus 2,000 equals 0. And the 2,000 divided by 4 pi. Now we could reduce that a little bit. That'll be 500 over pi. And then take the cube root. Okay, so that's going to give us the cube root of 500 over pi. Okay, so that's your radius. And then to figure out the height, we have the formula for the height. So the height will be 1,000 divided by pi r squared. Okay, and so if we have that's the radius, then the height's going to be twice this amount. Okay. And so that would be your dimensions to figure out the volume of a can with the least amount of cost for the metal. Okay, so this is a reminder of the first derivative test for absolutely extreme values. Okay, so just like we did in the earlier section with the first derivative test, we could use the critical number to figure out whether or not our value is an absolute maximum value or is it an absolute minimum value, just by doing the first derivative test. Okay, and I've shown you guys that repeatedly. You draw your number line, you put your critical value in the middle, or whatever critical values you have, and then you test each interval, right? So the interval to the left, in this case, you would test the value, you pick a number to the left of C, you pick a number to the right of C, you plug it into the first derivative, and then you figure out, is it decreasing then increasing? Then you have a minimum, or is it increasing then decreasing? Then you have a maximum. Okay, find the point on the parabola y squared equals 2x that is closest to the point 1, 4. Now the parabola y squared equals 2x, that's one of our sideways parabolas. It'll go through the origin. It's going to open to the right. Something like this. And then closest to the point 1, 4. Okay, 1, 4 will be somewhere out here. Okay, so for that, we want to figure out what is, and we're trying to figure out what's the point on the parabola closest to the point 1, 4. So we're trying to minimize this distance between the point and the parabola. Okay, so we're going to use a distance formula. Okay, and to start off with, we're going to replace x1 and y1 with 1 and 4. Okay, so we'll have d equals square root, and we'll just use x minus, in this case, x minus 1 plus, and then y minus 4 squared. So that's the main formula. Now the secondary formula will be the y squared minus 2x formula. So if we solve this for x, if we solve it for x, that means we'll divide by 2. That means x will equal 1/2 y squared. that means I can plug in for x, and that could help me get on my way. I'll have an equation all in terms of y, and I could easily take the derivative. Okay, so that means I have d equals square root 1/2 y squared minus 1 quantity squared plus y minus 4 quantity squared Now, one of the things we'll recognize real quick, to take the derivative of this will be a little complicated. We have an outer function of a square root, and then inside here we have more complicated functions. I'm going to work with the square of this. I'm going to work with the square of this distance. That's going to be a little bit easier to work with. Okay. And then I could relate it back to my original function. So from here, I want to take the derivative of these two terms on the right. Okay, so I'll have power rule, so that'll be 2 times 1/2 y squared minus 1 raised to the first times the derivative of the inside. Derivative of the inside would be 2 times 1/2, that's just 1y, plus 2 times y minus 4 times the derivative of the inside, which is 1. Okay, so what does that give me? If I distribute the 2 here, I get, and the y, 2 times 1/2 is 1. That'll be y cubed minus 2y plus 2y minus 8. Okay, so my derivative would be y cubed minus 8. Okay, so if I set that equal to 0, y cubed equals 8, so that means y equals 2. Okay, so pick a value less than 2, let's say 1. Pick a value greater than 2, let's say 3. Plug it in. 1 cubed is 1 minus 8, so that's negative 7, so that's a negative. 3 cubed is 27, minus 8, that's 19, so that's positive. So we go from a decreasing to an increasing. So this is a minimum. Okay, so that's good. So y is 2. And if y is 2, we can figure out what x is. Right, just plug into our formula on the parabola. Y is 2, so 2 squared equals 2 times x. 4 equals 2x. So x equals 2. X is 2, y is 2. So the point that minimizes the distance between parabola and the point on the parabola closest to the point 1, 4 would be 2, 2. And that would be the solution to that equation. All right, any questions on this? Just let me know. Email me. Okay, we'll practice some more in class. Have a good day. Have a good night. We'll see you soon.